In the previous lecture, we had discussed the eigenvalues of a complete graph and the eigenvalues of a complete bipartite graph. Now, today we will evaluate the eigenvalues of the cycle Cn. But before evaluating the eigenvalues of Cn, we will define what is a full cycle permutation matrix and how we can evaluate its eigenvalues, because then it will be useful in evaluating the eigenvalues of the cycle Cn on n vertices. So let's have this in the form of a proposition. So let's write a proposition. Let Qn be a full cycle permutation matrix. Be a full cycle permutation matrix. And then the eigenvalues of Qn then the eigenvalues of Qn are the nth roots of unity. Are the nth roots of unity. So let's prove this result. So here we have defined this Qn as a full cycle permutation matrix. So first we will assume a full cycle in Sn, and then we can construct this matrix Qn, and we will show that it is eigenvalues are the nth roots of unity. So let sigma be equal to A1, A2, so on An, Bn in Sn, be a full cycle. Be a full cycle. That is sigma is a cycle of length n. That is sigma is a cycle of length n. Then how we define the matrix of this Qn? Then the matrix of Qn, then Qn is a matrix Aij n cross n, where Aij is equal to 1 if sigma of Ai is equal to Aj, and this is equal to 0 if otherwise. If sigma of Ai is not equal to Aj, then we write the entry as 0, and we write the ijth entry of this Qn is equal to 1 if sigma of Ai is equal to Aj. So in fact, we can write the sigma in the row form as, so here our sigma is, here sigma, which is our n cycle A1, A2 through An. Then in row form, this permutation can be written in this way. In the first row, we write A row A1, A2, A3, so on, An minus 1, An. And then in the second row, we write the images of the Ai's. Now under this cycle, A1 goes to A2. Now A2 has the image A3, A3 has the image A4, and so on. Now An minus 1 has the image An, and An has the image A1. So therefore, when we construct the matrix of Qn, matrix of sigma, that is Qn, then 1, 2 entry will be equal to 1 because sigma of A1 is A2. The entry A2, 3 will be equal to 1 because sigma of A2 is A3. And similarly, the entry An minus 1n, that is the last entry in the n minus 1th row, that will be equal to 1 because sigma of An minus 1 is equal to An. And similarly, the first entry in the nth row, that is the entry A1 and An1, that will be equal to 1 because again sigma of an is equal to a1. So thus we can write this Qn. So Qn is an n cross n matrix. Now since a1 is not fixed, so therefore we have the entry 0 here. Now under that sigma, a1 goes to a2, so therefore the entry a12 will be equal to 1. Now a1 does not go to a3, so here we will have 0. And throughout, we will have all the remaining elements is equal to 0 in this row. Now second, here we have the entry a21, but a2 does not go to a1. Image of a2 is not a1, so here we will have 0. Now this is the entry a22, that's again 0, but now here we have the entry a23, and we know that sigma a2 is equal to a3, so therefore here we will have the entry 1, and so on. The remaining entries will be equal to 0. So in this way, we can see that the super diagonal entries are all equal to 1 in this matrix. So let's consider the n minus 1th row number n minus 1. So here, this will be 0 because an minus, this is the entry a1, n minus 1. So this entry a n minus 1, 1. Similarly, here we will have 0, then 0, and then so on. And the last entry in this row will be equal to 1. And this last entry is the entry number a n minus 1 n. And we know that sigma an minus 1 goes to an. So therefore, this entry is equal to 1, and all the remaining entries in this row will be equal to 0. Now here, the entry here, its coordinates are a, its position is a, n1. And by the definition of the n cycle, now here we see that an goes to a1. So the n1 entry will be equal to 1. So here we will have 1. Now here we will have similarly 0, 0, and so on. All the remaining entries will be 0 in this row. So therefore, this is the matrix Qn. We can clearly see that Qn is orthogonal. Qn is orthogonal because we can see that the products of any two rows is equal to 0, and the sum of the elements in any row or in any column is equal to 1. So all these rows and columns are the unit vectors from Rn, and in fact they actually form the standard basis. Like if we first take the second column, then third column, then n minus 1 column, and the last coordinate as the first column, then this is actually E1, this is E2, so on. This is En minus 1, and this one is E1. Then this E1, E2, En minus 1, E1, they are the n tuples from Rn, which are actually forming the standard base of Rn. So these vectors are linearly independent and they are orthogonal to each other. So this matrix Qn is actually an orthogonal matrix. And once we have this matrix Qn as orthogonal, then orthogonal means that Qn inverse is equal to Qn transpose. So therefore, our matrix Qn is this matrix, and this was obtained from the permutation sigma, which was chosen to be an n cycle. Now again, let's have a look at this permutation sigma. Now, sigma is an n cycle. Then, thus order of sigma is equal to n in Sn. So that is, n is the smallest positive integer, n is the smallest positive integer such that sigma power n is equal to the identity permutation E. Here we will not denote this identity permutation by I, because here I will denote an identity matrix that we are going to use in the next step. So therefore, sigma power n is equal to identity permutation, and sigma power anything less than n is not equal to identity. So now, since this Qn is a permutation matrix is a matrix of the sigma, and sigma power n satisfies to be equal to identity, and then we can clearly see that this, when we multiply this matrix Qn n times, we will get Qn power n. will be equal to the identity matrix. So this gives us that Qn power n is equal to the identity matrix of order n, and Qn power anything less than n is not equal to identity. So therefore, since this sigma is a cycle of length n, its order is equal to n. So n is the smallest positive integer satisfying sigma power n is identity. So that means Q power n must be equal to the identity matrix. So thus we have the equation. So thus we have Qn power n is equal to identity. Now this n, which is in the subscript, it actually denotes this Qn is a full cycle permutation matrix on n symbols, and this power n, this denotes that we are multiplying this Qn n times. Now we will get this equal to identity matrix. Now from this equation, so this gives the polynomial, f of x is equal to x power n minus 1 is the minimal polynomial of Qn. Because we have already seen that this n is the smallest positive integer such that Qn power n is equal to identity. So this means that we cannot reduce this polynomial f of x to a degree less than n, which annihilates this matrix Qn. In fact, we can see that f of Qn is equal to 0. So that is what we are observing here. That is f of Qn, which is equal to Qn power n minus 1 is equal to 0. And where n is the smallest possible integer, positive integer with this property. So we have obtained the minimal polynomial of this matrix Qn, but now since Qn is a matrix of order n, and since its minimal polynomial is a polynomial of degree n, this clearly means that the characteristic polynomial of Qn is equal to x power n minus 1. So thus, the characteristic polynomial of Qn is C of x, which is equal to x power n minus 1. So therefore, the eigenvalues of Qn are the nth roots of unity. So therefore, we have obtained the roots of this full cycle permutation matrix. And we have seen that its eigenvalues are the nth roots of unity. So now we will compute the eigenvalues of the cycle Cn. So now this theorem, for n greater or equal to 2, in fact for n greater or equal to 3, because the cycle with the smallest possible length is 3, for n greater or equal to 3, the eigenvalues of Cn, eigenvalues of the cycle Cn are 2 cos 2 pi k by n. 2 pi k by n, where the k has values from 1, 2, up to n. And where the Cn is a graph on n vertices, where Cn is a cycle on n vertices. So the proof. Now, in order to prove that the eigenvalues of the Cn are these, we have to show that the eigenvalues or the adjacency matrix of Cn are twice cos 2 pi k by n for these n values of k. So for that thing, we will try to look how the adjacency matrix of the cycle Cn will look like. Now, before doing that, we will have a look on the cycle Cn. So let's construct a cycle here. So let this be the vertex C1, sorry, the vertex V1. Let's call this as vertex V1, V2, V3, V4, V5, so on. Let this be the vertex Vn, and let this be the vertex Vn minus 1. Then let this be our cycle Cn. Let Cn be defined by V1 goes to V2, and this is adjacent with V3, and so on. And last we stage Vn, V1. Let this be our cycle Cn, that is Vi is adjacent with Vi plus 1, where I runs from 1 to up to n minus 1, and Vn is adjacent with V1. So this is how we define the adjacencies in the cycle Cn. Now, if we want to construct the matrix of the cycle Cn, so then adjacency matrix of Cn will be a matrix A, I, J, n cross n, where Aij is equal to 1 if I is equal to j plus 1 or j is equal to I plus 1. Because we have the adjacencies like this, Vi and Vj are adjacent. So actually we have this in the cycle Cn, we have the vertex Vi is adjacent with the vertex Vj when we have defined the cycle in this way. Then either this Vi should be equal to j minus 1. Either I is equal to j minus 1 or j is equal to I plus 1. So that is what we mean by writing that either I is equal to j plus 1 so it is j minus 1 here. So it is j minus 1. That is j is equal to I plus 1. And in fact, we can use these statements here. So better to write like this. If Ij belongs to this set, it is 1, 2, 2, 3, so on, n minus 1, n, or n, 1, or the reverse. It is 2, 1, 3, 2, so on, n, n minus 1, and 1n. So because whenever we have, if we have V1 is adjacent with V2, then V2 is also adjacent with V1. So if I is equal to 1, 2, I is equal to 1, j is equal to 2, then we can choose the reverse also because V2 is also adjacent with V1. So therefore 1, 2 should be here and 2, 1 should also be here. Now 2 and 3 are adjacent, 2 and 3 are adjacent, but 3 and 2 are also adjacent, so 3 and 2 are also adjacent. Similarly, we have to take the ordered pairs in both the ways. And this is equal to 0 otherwise. So therefore, we can see that the adjacency matrix of C, and now when we visualize the matrix Q and the full cycle permutation matrix, that will have its ijth entry equal to 1 if ij belongs to either 1, 2, or ij is equal to 2, 3, or ij is equal to n1. So up to this stage, from 1, 2, 2, 3, up to n1, these are the values of the ij, where the ijth entry is equal to 1 in the full cycle permutation matrix. But now, when we look at these entries, 2, 1, 3, 2, up to 1n, these are actually the entries which are the reverses here. Here we have 1, 2, but here we have 2, 1. So that actually, in terms of matrix theory, defines as something like the transpose. So if we look for the transpose of the matrix Qn, that will have these as its non-zero entries. In the transpose of Qn, 2, 1 will be a non-zero entry because 1, 2 is a non-zero entry in Qn. And again, 1, 2, 3 is a non-zero entry in Qn. So therefore, 3, 2 will be a non-zero entry in Qn transpose. And similarly, up to n1, this entry is a non-zero entry and has the value 1 in Qn. So therefore, 1n entry has the value 1 in the Qn transpose. So therefore, we can see that the adjacency matrix of Qn is actually Qn plus Qn transpose. So thus we observe that adjacency matrix of Cn, this is actually equal to Qn plus Qn transpose. But now, since this Qn is an orthogonal matrix, so this is equal to actually, this is Qn plus Qn inverse, because Qn is orthogonal. Because Q is an orthogonal matrix, so therefore Qn transpose is equal to Qn inverse. But now here we can use the spectral mapping theorem because we know what are the eigenvalues of Qn, and clearly the eigenvalues of Qn inverse, since this Qn is an invertible matrix, so the eigenvalues of Qn inverse are the reciprocals of the eigenvalues of Qn. So now, from previous proposition, the eigenvalues of Qn are 1, omega square up to omega power n minus 1, where omega is the nth root of unity. So nth root of unity means that omega power n is equal to 1. So thus, since all of these are the non-zero eigenvalues, so thus the eigenvalues of Qn inverse are 1, the reciprocals of these, it is then omega power minus 1, then omega power minus 2, and so on, omega power minus times n minus 1. So therefore, using the spectral mapping theorem, so therefore, using the spectral mapping theorem, on the equation adjacency matrix of Cn, which we have written it is equal to Qn plus Qn inverse, we have So what we have, we will substitute, if we substitute 1 here, we will get 1 plus 1, that is 2 is as an eigenvalue. Then omega plus omega inverse, then omega square plus omega power minus 2. And similarly, the last eigenvalue will be omega power n minus 1 plus omega power minus times n minus 1. So that is the set of n eigenvalues for Qn plus Qn inverse. So now, but before doing that, now as observing that omega power k into omega power n minus k is equal to 1. Actually, this is equal to omega power n, and that is equal to 1. Thus, inverse of omega power k is omega power n minus k. So therefore, the eigenvalues of adjacency matrix of Cn are omega power k plus omega power n minus k, where k runs from k is equal to 1 to up to n. So these are the eigenvalues of adjacency matrix of Qn. But now, since omega is the nth root of unity, so therefore this omega power k, or we can write this omega power k, this is equal to e power 2 pi I k by n. And then omega power n minus k can be written as omega power minus k. So this is actually equal to omega power k plus omega power minus k, because omega power n minus k is same as omega power minus k. So here we can add this term as e power minus 2 pi I k by n. Now, this equation, we know this is equal to, in terms of cos and sine, we can write it as, this is cos 2 pi I k by n. So this is equal to cos 2 pi k by n plus I sine 2 pi k by n. So this is the first term. Now similarly, the second term is cos 2 pi k by n minus I sine 2 pi k by n. So these are the eigenvalues of, so these are the eigenvalues of adjacency matrix of Cn. But now this equation gives us 2 cos 2 pi k by n, where k is equal to 1, 2, so on up to n. So therefore, the eigenvalues of the adjacency matrix of Cn, they are twice cos 2 pi k by n. Okay, so with this thing, we will conclude today's lecture. Thank you so much.